In this set of videos, we're going to look at how carbonyls such as acetone react with alcohols to make hemiacetals or acetals. So I'm just going to use the simplest alcohol I can, methanol, and then in an hydronium or an acid environment, what's going to happen is that C double bond O is going to break, and you're going to end up with an OH on one side and an ether or a methoxy group on the other. This functional group is called a hemiacetal. So that's our direction that we're going to go. Now, remember when we do any mechanism with carbonyls, C double bond O's, the C is electrophilic, so it will draw in nucleophiles. So when you look at this, you always have to look for the nucleophile that will attack at this carbon. Now, why is it electrophilic? Two different reasons. You have polarity going for you with the oxygen more electronegative, and you also have resonance. So because of resonance and polarity, this carbon is electrophilic. Well, the nucleophile that's going to attack right here is the O on the methanol. And we also have an acid catalyst. Now, you should be able to, after we do this mechanism, take this mechanism and go backwards. So we're going to just walk through this mechanism. Now we know where we're headed. And the first step is to use our catalyst. We do that, we're actually making that carbon even more electrophilic because now we have an overall positive on the species. And then in comes our methanol attacking the electrophile. And when we're done, we've broken the pi bond, so we have OH on one side and our protonated methoxy group on the other. And the last step, here's the water that we formed. The last step is the water comes in and regenerates the catalyst. Now that in itself is not that interesting. It's much more interesting and it has more biological implications when you look at ring closing mechanisms of hemiacetals. And later on in this video, I'll show you glucose, which does the same thing as what I'm going to show you right now. So when you have your alcohol tethered to your carbonyl, such as in this mechanism or this reaction, what's going to happen is we're going to have a ring closing event. 1, 2, 3, 4, 5. So if we look, let's look for this pattern. Let's figure it out before we even start the mechanism. So 5-membered and 6-membered rings form preferably. 4-membered are too small, and 7 members are too big. It's sort of like the 3 bears. Not too hot, not too hot, not too cold. So 5 and 6-membered rings are what you always look for. So if we look at this, this is going to be, let's call this oxygen 1, 2, 3, 4, 5. So this nucleophile is going to hit this carbon right there. So it will be a 1, 2, 3, 4, 5-membered ring. So let's draw that. So if this is going to be our carbon number 1, 1 is attached to 2, to 3, to 4, there's 4, to 5. 5 will still have its methyl group. 5 will become the OH. And there's the new bond that will form. So this is the hemiacetal right there. That's the carbon that was the carbonyl that will form. So let's run through this mechanism, just like above. So again, here's our hydronium. Protonate the O. A couple hints. Whenever you have something like this, a lot of times people will go over and protonate this thing and get totally lost and not know where they're going. If you have 2 O's in a structure, protonate the O that doesn't have the H first and see how that works for you. So now when we're done, you have to redraw it. And we have now our protonated carbonyl. Here comes the nucleophile closing the ring. And let's set it up so it looks just like that one. We have the O, it still has an H on it. And then our 5-membered ring still has a methyl group. Now this is the OH. And there, this will have a plus. And the last step is taking our water and reforming the hydronium catalyst. So that is a ring closing mechanism. Now let's take another one and go backwards or forwards, depending on your point of view. I have another acetal prepared for you. Now this is a 6-membered ring, and let's put the O here and the methyl group here and an OH here and then a methyl group here. So now we have to try to figure out what's going to happen. So look for the carbon that has 2 O's attached to it, and that's going to become the C double bond O. So this time I'm going to count this way. 1, 2, 3, 4, 5, 6. So there's 7 carbons total. I'm not going to count that oxygen. So when we're done, 1, 2 has a C double bond O, 3, 4, 5, 6. What is on 6 is our OH, and 7. So now we're going to open this ring up. How you do this? Well, here's our O that doesn't have an H. And remember, this is actually not an equilibrium arrow. Let's get rid of that. Sorry about that. I'll just erase it. And then draw the arrow, H3O plus. So now what we're going to do is we're going to take our H3O plus, I'll do it up here, draw it out, and our O will pick that up. Next step, I know it gets tedious, but you always have to redraw it. Don't forget your carbons, and it's really easy to add and lose carbons as you do a mechanism. So now we have OH. And now what we've just done is made this into a good leaving group. Well, in my class, I always say, what do leaving groups do? Well, they leave. Well, let's make it leave. I'm making it leave by forming the C double bond O, and that bond breaks. There goes the leaving group. And so now we are one step away from being done. So here I open the ring up, and now I have our H right there. And let's count the carbons. It should make sense. 1, 2, 3, 4, 5, 6, 7. There's 6 right there. There's your methyl group, and 7. And then the last step is to deprotonate the carbonyl. Okay, I'm going to erase the screen and just show you glucose. So take some time or pause the video so you can make sure you have it, because it's going to go away in a second. Well, the whole reason why hemiacetals, I think, oh, that was ugly. Whole reason hemiacetals are important, not much better, but here you go, is in the realm of biology, you have hemiacetals all the time. And most of you have seen glucose as a ring and not as an open chain. Oh, that was dumb. Here we go. This is glucose, and it's in equilibrium with its ring closed structure. Now this is a Haworth projection, so you're looking sideways at the ring, down, up, down. So this is what most of us in our bio books see glucose to look at. This is called beta D glucopyridose. Well, it's a hemiacetal right there. That's carbon number 1. Why do you know that? That carbon has 2 oxygens attached. 1, 2, 3, 4, 5, 6. That's the carbon. So if this is 1, 2, 3, 4, 5, 6, the carbon that closes the ring is that carbon right there. So if you look at the stereochemistry of glucose drawn as the Fisher projection, this is right, left, right. And when you spin it 90 degrees into the Haworth projection, you get down, up, down. And the beauty of glucose, or beta-D-glucose, and it's beta because this carbon right here, this OH, can either go up and down. When it's in the beta position, it's the most stable. So if you draw a chair for glucose, what you get is all of your OHs are in the equatorial position, and it's the most stable. So this little thing ties everything together, first semester, second semester, and then biochem. And that's why I think hemiacetals are way cool.